Okay, homework question on number 3.
I have a question on the last one. You have to like divide by. You have to like divide by 22.
This one?
I got it.
Yes. Okay, so they are asking you to give a function y in terms of x. So your output has to be y, so that should lead you to look at this problem, y equals 3t plus 5. But they want it in terms of x. That means your input needs to be x. Right now, what is the input? T. We don't want it to be t, we want it to be an x. So how can we take t out and replace it with some expression that involves an x? Yes. Take your x equation and solve it for t. So you'd have x over 21 equals t squared. So you would have to take the square root, plus or minus, right, when you put a square root in. Okay, and then you could plug that in for your t. And I'm assuming they probably didn't have you use the plus or minus, just 3 square root. So that would be your answer. Are we okay with that? Yes. Okay, so there's graphs of f and g. We want to think about the function f of g. So remember, that is just alternate notation of this. So first you're evaluating the inner function g of x, and then using that output as the input into f. As x increases from x equals -2 to x equals 0. So we are looking at our g function first, looking from -2 to 0. What are those y values going to be? From 0 to -2. Okay, so when your input to g is -2 to 0, your output is 0 to -2. Are you guys with me on that? Yeah. So now that is what you are plugging into your f function. So from 0 to -2, what is happening? Yep. Right, you have to read it from 0 to -2 because that's the way this one is. So it's decreasing that direction. The x values, yes. Yes, they're your inputs. You're always looking at the input. And then you're checking what the output's doing. You okay with that? That concept? Yeah. Okay. Anything else on the homework? Nope. Okay. Let's do our lesson then. How'd the pre-class go? Pretty good? All right. Easy. Okay, we are all about inverse functions. Remember, this is the last section, the last investigation in this module, so test is coming. All right, how do you undo plus 10? Absolutely. So if you had f of x equals x plus 10, then the way you would undo that would be by subtracting 10. So let's define a separate function, g of x equals x minus 10. Okay, so let's go ahead and compose those. Let's do f of g of x. How do you do this problem? If I ask you to find f of g of x, what are you going to do first? Okay, so we're not going to do anything with f, but we're going to plug g of x in, which is x minus 10. Then your problem reads, find f of x minus 10. So x minus 10 gets now plugged into the f function for the x. So it's x minus 10 plus 10, which is just what? What was the input in this original problem? X, right? X was the original, most original, very first input. What's the output? Ooh, that's interesting. The input and the output are the same. What? All right, let's try the composition of functions in the opposite order. G of f of x. What's your original input? It's x, right? That's your first input. We can't do anything with just x, so we do f of x. F of x is x plus 10. So now your problem reads find g of x plus 10. And that means take x plus 10 and plug it into your g function for the x, which is x plus 10, what? Minus 10, which is x. What's your output? So in both composition of functions, both orders, the input and the output are the same. Whatever one function did to x, the other function undid it. Does that make sense? Think about that sentence. Whatever one function did, the other function undid that operation, or those operations. These are called what? Inverse functions. Inverse functions, excellent. So what is an inverse function? Between two covariant quantities, so two quantities that change with each other, but with the input and output quantities reversed. Okay? So here's what we just said. If G is the inverse of F, then G undoes the process of F. And F undoes the process of G. So they both have to undo one another. So G of F of X has to equal X, and F of G of X has to equal X. You guys with me on that? Notation for an inverse. If F is the original function, its inverse is F to the negative first power. That is just notation, though. It doesn't literally mean take it to the negative first power. So when you see this, you read it as F inverse. It's weird, but that's what it means. So in this, whenever you're talking about inverse functions, we say this F inverse. It is not necessarily equal to 1 over F, right? Isn't that what a negative exponent really does? Drops it to the bottom. But that's not actually what we're saying here. It is just the notation. That's just how we write it. It is what it is. Okay. See how your pre-class was related to this idea of inverse functions? Did you see the parallels? Okay, so they had you solve it for the opposite quantity. So first it was F in terms of C, and then you had to write it C in terms of F. Your inputs and your outputs switched. So in the original function, your input was C, but now your input is F. Your output was F, now it's C. So that is exactly what we're saying in this first definition. The input and the output reverse. Part B, they just had you rename it as G. Same thing with that. Any questions on the pre-class? So were those two functions, G and H, are they inverses? Yeah? Cade, they're inverses, right? Yeah. Notice that on part E, or on E, part 3 and 4, you found H of G of 100. What was your output? It was still 100. When your input was 212, the output's still 212. So if you put a number into a composition of functions that are inverses, you should get the same input as your output. Everybody good? Okay. So how do you verify then that functions are inverses? What would we just say? Sometimes they're more complicated. You just ask them and you tell them. What'd you say, Camden? Yes, but what's the easy way to check that with function notation composition of functions? Would we just show you on that pre-class, the last part? Yeah, you find the composition of functions and what should it equal? Yes. And you have to be able to do it both ways. So f of g of x has to equal x, and g of f of x has to equal x. Or whatever input you plug in, the output has to equal that as well. Okay, so let's try one. Let's verify. This is number 10. Your classmate believes each of the following pairs are inverses and thus use inverse function notation to define them. Is your classmate correct? Verify by creating the formula for f inverse f of x. So they are saying that these two are inverses. So this is like our g of x, but they're actually using the inverse notation because they are saying, yeah, this is already an inverse. To check it then, you need to do two things. You need to find f of f inverse, and you need to find f inverse of f. Okay, so let's check. This one, you're working from the inside out, so you're first going to have x plus 8 over 2 minus 1. You are going to take that and plug it in where? You just are so thrilled to answer those questions. X plus 8 over 2 minus 1. Guess I should use a bracket there. Plus 1 minus 8. Oops, this is a bracket. Because it's double parentheses. If you just want to stick with parentheses instead of brackets, that's fine. That's cool. All right, so simplify it. Well, negative 1 plus 1, those are going to be gone, right? 2 times 2, well, or 2 over 2, that's gone. And x plus 8 minus 8 is just going to leave you with x. Does that mean those are inverses? No. Not yet. You still have to check the other way. It's got to work both ways. So f inverse of, now you're going to do 2 times x plus 1 minus 8. And you might choose to maybe simplify that first. So that would be 2x plus 2 minus 8, which is 2x minus 6. And then plug that into your inverse function. So we've got what? 2x minus 6 plus 8, all of that over 2 minus 1. Everybody with me? Yeah. Okay. 2x plus 2, when I combine negative 6 and 8, all over 2 minus 1. Little distributing of division there gives you x plus 1 minus 1, and oh, look at that. That's x. So if both of the compositions, both of them come out to be x, then what is true? Now we know they're inverses, and that work right there verifies that that is true. That proves they are inverses. Any questions on verifying inverses? No? Excellente. Continue. Oh man, calm yourself. All right, number 5, the function f gives the volume v of a sphere in cubic inches as a function of its radius r in inches. The function formula is f of r equals 4/3 pi r cubed, with v equals f of r. Side note, anybody know that formula, volume of a sphere, off the top of their head? No. Gotcha. It's on your paper, you know. Just wondering, because, you know, sometimes kids in calculus don't know things. All right, anyway, yeah, you would be given that. Part A, removing the function notation produces the formula v equals 4/3 pi r cubed. Okay, so, okay, they changed f of r to just a v. Solve this formula for r and explain what the new formula represents. How do we solve this formula for r? What would be the first step? Okay, so 3/4 v equals pi r cubed. Divide by pi, And that's the same, dividing by pi would be the same as multiplying by what? 1 over pi. So that would now become, I'm going to come down here so I'm not on all those words, would become 3 over 4 pi v equals r cubed, and then cube root it. So the cube root of 3/4 pi, pi in the denominator, of v equals r. What does that represent? No. Okay, this represents the radius in terms of volume. Good. It is radius in terms of volume. Okay? Let G, part B now. Let G be the function that inputs a sphere's volume and outputs its radius. Wait a minute. Didn't we just solve for that? Okay, so we can let G of V equal the cube root of 3 over 4 pi times V. Use function notation to define it. There we go. We've got it. Explain what each of the following represents in this context. We don't actually have to evaluate. What is f of 40? But what does it represent? The volume. F of 40 represents the volume when R equals 40. What does G of 40 represent? The radius when the volume is 40. Hey, Maddie. What can I do? Hurry up. And then these are the same things, they've just actually given you the numbers, right? So f of 7 would be the volume when your radius is 7, and g of 2.14 equals this. This would be your radius when your volume is 2.14. Are we okay with that? Okay. So that brings us to, how do you find a function's inverse? And that is very similar to what we just did. So if we have f of x equals 4x plus 3. F of x, remember, is just y, right? Okay. What you do is you switch your x and your y's. So y becomes x becomes y. Switch your x and your y's, and then solve for y. So you would subtract 3 and then divide by 4. The inverse of 4x plus 3 is x minus 3 over 4. Isn't that what we basically just did over here? Didn't we just solve for the other variable? When it's word problems, you don't have to worry about switching your x and your y. Okay, so you just go ahead. If it's variables other than x and y, just solve for the other variable. That's all you're doing. Okay? All right, use the given table. Let's do some yeah, I sure can. Rewind to this. How do what, Michael? So the real idea is that you're going to solve for the other variable. Okay? But when we're solving for the other variable, it makes sense to end up having a y equals, having y in terms of x, when it's just an x and a y. When it's a real world situation, other variables, you don't have to think about doing that. It's just when you're dealing with basic x and y. But the whole idea is you're going to solve for the opposite variable that it's already solved for. Okay. All right, let's be able to do these off of a table. So first of all, what is just f of 0? What is the input? 0. What is the output? 4. So f of 0 is 4. Okay, I left off the, quiet guys. I left off the directions up here that say f and g are inverses. Okay? F and g are inverses. So that means that g is the inverse of f, and f is the inverse of g. Okay, so you could alternatively write these. So what is g inverse of 3? -2. What's g inverse of 0? Okay, wait, rewind to B. Rewind to B. Remember that f and g are inverses. So if we are looking for the inverse of g, what is the inverse of g? It's f. Okay, so when your input is 3, the inverse of g would give you -2. So keep going. All right, what's inverse of, guys, inverse g of 0? 4, and inverse of f of -1. Yeah, it's not right. This is right. Are we okay with that? Yeah. Use the given table to evaluate the following here. Yes. So the inverse of g of 3 is what? Of 3, -2, yes. The inverse of g of 0, 4. Okay, now check this one out. First do g of 2. What does that give you? Careful, what is g of 2? It's not 6. That's f of 2. It's -1. Okay, then what's the inverse of -1? F inverse of -1. It's 3 either way there. Okay, how about this one? So first of all, you'd be looking for f inverse of 6. Well, f inverse is the same as g. So what's g of 6? What? It's not there. So what would we say? It doesn't exist here. Okay. All right, now we have to figure out how to graph or sketch an inverse. Okay? On this one, that's problem number 7. So your graph is this part, the ones that has the ordered pairs listed. They also have drawn the graph y equals x. The way you sketch a graph of an inverse is you reflect your function across the line y equals x. So there's your line of reflection right here. Oh my gosh, we're not going to do that. One way you can do it is to switch. Well, first of all, can you see where this would go? Like if I'm sketching this, if I push it, it goes this way, right? Okay, that would be that part. What's this ordered pair? 0, -1. Compare that to this point that was its point that was reflected. Your x and y are flipped. They're inverses. Okay, so you can also just switch your orders pair. So 1, 0 should be a point. And 2, 1. It's always y equals x. So anytime you are finding the graph of the inverse, you always reflect it across y equals x. That's why that's drawn on all of these. I don't think you need tracing paper. If you really want to use it, you may, but okay. All right, so let's look at number 8. So you can do this one of two ways. You can think of just what's the reflection going to look like, or you can take your ordered pairs and switch your x and your y. Just like we were saying, to make an equation's inverse, you switch x and y. You do the same thing with the ordered pairs. So negative 1, 0 should be a point, and 0, 1 should be a point, as well as what else? 1/2, 2. Okay? Mine's not perfect, but okay, so you can think of it maybe both ways. And then this one would stay the same, right? Because it's negative 2, negative 2. Okay, over here, negative 1, still going to be the same. But watch how this one reflects. So now this one comes like that, right? And this point that's 2, 1 is going to become 1, 2. A double helix. Negative 2, 1 becomes 1, negative 2. The point 0, 0 would stay as the point 0, 0. And then this would come up. Oh, yeah, that's not right. Hold on, I didn't do that right. That would come. Wait a minute, what did I do wrong? That's right. Negative 1, 1 would be here. Is that right? That would flip here. That would flip there. Yes. Wait, something's wrong. What's wrong with me? Wait. Yeah, this doesn't go here. Yeah. So this would be 1, negative 2 here. So yeah, that would come and then go like that. It's so ugly. Which way am I doing it wrong? Why can't I picture what it looks like? Somebody go up to the board and draw it. Oh, it'd go like this. Got it. Sorry. Was not visualizing that. Thanks. I just needed your support up there. Thank you. Okay, do the last two. Take 1 minute here and do the last two on your own. Okay, check yours against mine. Did you get what I got? I didn't do it wrong this time. Good stuff. Any questions? So if you want to graph a function's inverse, you must reflect it across what line? What line is it? Y equals x. Alternatively, you can switch the x and the y for all of the ordered pairs. However, sometimes the inverse is not actually going to be a function. So let's take a look at y equals x squared. What is f of 2? 4. What's f of negative 2? Also 4. Is y equals x squared, is that actually a function? Is this graph a function? Yeah. Absolutely. Absolutely. Different ways we know that. For one, it's written in function notation. They're not going to write something in function notation if it's not a function. Secondly, it passes what test? Vertical line test. Each input has only one output. But does each output have only one input? No, because look, I have outputs of 4 with 2 different inputs. Okay? Imagine reflecting this across y equals x. Okay, what's it going to look like? It's going to be a sideways parabola. Not the perfect drawing there, but would that be a function then? No. Why? It doesn't pass vertical line test. And remember, the other way you can think of this, we had the original points negative 2, 4, and 2, 4. You would have to switch those. They'd become 4, negative 2, and 4, positive 2. Does each input have exactly one output? No, I have the same input with two different outputs. You guys following me on that? Okay. Part C is talking about you could restrict the domain. So if we only reflected or only dealt with half of the parabola, we'd be okay. So if I limited it to just the right side of this parabola, then I would only have the top half of this parabola, then we could make it a function. But the entire function would not be. Okay? So here is all of that written out. Remember, a function has each element of the domain paired with exactly one element of the ooh, I used the wrong word there, range. Change that on your paper. I wrote domain twice. A function has each element of the domain paired with exactly one element of the range. Every x can only go to one y. Every x goes to exactly one y. New definition. A one-to-one function goes the opposite way. A function that has each element of the range paired with exactly one element of the domain. So you've got to check your y's and make sure they only go to a single x. The vertical line test tests whether something is a function. But now we have the horizontal line test, and that tells you whether a function is one-to-one. Do you guys remember, I forget what we did, and you guys were talking about using a horizontal line test? It wasn't this class. It must have been 8th period. So don't worry about that. But anyway, so if you look back at this original graph, the graph of y equals x squared, would that pass the horizontal line test? No, right? It's not going to pass horizontal line test because it's going to run into more than one point on all of these lines. So what does that tell you? It's not a one-to-one function. Is it a function? Yes, because it passes vertical line test, but it is not a one-to-one function because it does not pass horizontal line test. Correct. So the conclusion is if a function is one-to-one, its inverse is also a function. But if a function is not one-to-one, its inverse will not be a function. Got it? One-to-one functions, their inverses are also going to be functions, and that's the takeaway of what you need for to know about one-to-one functions. Any questions? Okay. All right, so for each of these two graphs, first of all, is it a function? Yes. Is it a one-to-one function? Does it pass horizontal line test? Absolutely. So is its inverse going to be a function? Yes. Everybody good with that? Okay. Part B, is it a function? Yes. Is it a one-to-one function? No. So is the inverse of this function going to be a function? No. What could we limit the domain or restrict the domain to be so the inverse would be a function? From -2 to where? Nope, because it would still fail the horizontal line test there. Oh, -infinity? Sure. So you could restrict it here, and that part of it would give you an inverse that is a function. Where else if I was looking in this direction? Yep, so you can either do from -2 to 2, and that part would be good, or from 2 to infinity. So you want to find places where it's going to pass the horizontal line test. Yes, on this particular problem, they're saying choose one restricted domain that would work. So you can either have from negative infinity to -2, or -2 to 2, or 2 to infinity. Yeah, I guess technically you should have brackets here because you can include those places. Everything good here today, guys?
Yeah.
Excellent. So, did you read the last? No, that's just extra practice. You don't have to worry about this. Okay, here's things, really important things. Homework 15 tonight. That is the only thing on iMathis. There is no more pre-class because we're done with the whole module. You have a take-home quiz today. You will most likely, this second period will not have class tomorrow because we'll still be at the evacuation drill. 8th period, talking to people watching the video, will not have class because we have our pep rally tomorrow. So this quiz, though, however, is still due tomorrow. So even though we are not having class, you need to come in this room and turn in your quiz sometime tomorrow. Got it? Otherwise, it's a 0. Everybody turn in your quiz tomorrow. 2 questions. And it's not what we did today. It is difference quotient. It's all difference quotient stuff.
Wait, that's what we had the one question.
Yeah.
Oh, that's easy.
The exam will be on Tuesday. I had previously told this class, second period, that it was going to be on Monday. It is going to be on Tuesday. Okay, since we're not having class on Friday tomorrow, we will review on Monday, test on Tuesday. Your review problems in iMathis will open tomorrow morning. They will be due on Tuesday. However, just like on the last test, make sure you look at the problems before class on Monday. So if you have any questions, you can ask them. Otherwise, you won't get a chance to ask them on Tuesday. Any questions on what is happening? Okay.